Most viral robot demos are cherry-picked moments that hide the physical reality of latency, sensor noise, and mechanical inertia. They show a perfect execution but omit the 90% of time spent on error correction or simulation to reality gaps. You see smooth motion in marketing videos while the real world looks broken. Today we unpack the engineering story behind this disconnect. The gap between a polished demo and deployment is not a lack of intelligence. It is an engineering constraint regarding physical uncertainty. The first bottleneck lies in what engineers call the simulation reality gap. Standard robot programming relies on perfect CAD models where lines are straight and surfaces are flawless. In the real world, environmental uncertainty breaks these assumptions immediately. A study from the University of Porto highlights that while a demo might show a path generated from a clean Autodesk Inventor file, actual deployment requires sensory feedback loops just to correct for calibration errors and physical inaccuracies that simulations ignore. The robot assumes it is standing on flat ground when in fact there are millimeter-scale variations or dust particles that disrupt the balance. This means the perfect lines you see on screen do not exist outside a computer. When we move from geometry to intelligence, we encounter what researchers call the AI fluency illusion. A March 2024 study using Unity VR and GPT-4 reveals a critical mismatch between human expectation and machine capability. 12 participants took part in this user study evaluating communication strategies, and they assumed LLM-powered robots could handle complex reasoning tasks effortlessly. In reality, users stuck to simple scripts because the system struggled with variable autonomy under real-time constraints. The demo highlights language fluency while masking the underlying latency or sensor failure points that prevent a robot from understanding nuanced commands without crashing. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This illusion creates a dangerous perception where fluent speech equals reliable action. A participant might ask a robot to rearrange a cluttered table, and the system responds with perfect verbal confidence. However, the physical execution often fails because the AI cannot process the visual complexity fast enough to coordinate the actuators before inertia takes over. The study found that while humans thought they were talking to a genius robot, the interaction was essentially limited to basic pre-scripted motions because the cognitive load of processing natural language in real time overwhelmed the control loop. The third major hurdle is what we call the training wall. Teaching a robot appears simple on video, but becomes a nightmare when you try it with actual hardware. Current systems force humans to repeat entire tasks even when a robot knows most steps. A study by Diehl and colleagues at Chalmers University of Technology, in collaboration with IBM, found that without specific algorithms, robots cannot identify the single missing step in a sequence. This forces redundant training where users must re-demonstrate 72% of a task they already know because the system lacks an excuse state algorithm to isolate the gap between known and unknown skills. This inefficiency means that if you want to teach a robot a complex assembly line operation, you cannot just show it once or twice. You have to go through 90% of the process again every single time because the machine treats your new input as a total rewrite rather than an update. The research indicates that without targeted learning methods, we are wasting massive amounts of human effort trying to bridge this gap. The system does not know what is missing. It only knows that something went wrong and needs to be shown again from scratch. These three bottlenecks, simulation chaos, AI latency, and redundant training, are the invisible walls stopping robots from leaving labs and entering factories or homes. They are not problems of computing power alone, but fundamental issues with how we model physical uncertainty. We cannot simply software update our way out of gravity or friction. The hardware must be robust enough to handle variants that no CAD file can predict, and the control systems must learn faster than humans can demonstrate every single variation. The path forward involves developing excuse states where robots know what they already understand versus what is new. New research on vision language models shows promise in translating raw visual data into precise actions, but it still struggles with sensor noise compared to simulated environments. We are moving towards systems that use sensory feedback loops not just for correction but for active learning of the environment's chaos. Until these physical constraints are solved, Every viral demo will remain a highlight reel rather than a preview of daily life. The reality is that we are building machines that must operate in a world designed for biology, not precision engineering. The delay in deployment is not because robots lack brains, it is because they have bodies that react to friction and dust the same way humans do. We need to stop expecting magic from marketing clips and start demanding transparency about the physical limits of these systems. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.